And here comes the more fundamental idea that I would like to discuss today. So, well, the previous direction is just a preview, so we will come back in a couple of weeks later. But a more important part is understanding the concept of matrix. So every matrix can be understood as a linear transformation. So let's try to find what it means. So let's recall the previous matrix multiplication. So given the coefficient matrix, we wanted to find the unknowns. And here comes the target output. So we built AX equal Y, and we can expand it using the original matrix. So like we discussed it, we can build a system of linear equation to find x0 and x1. And you can try to look into the same problem in completely different ways. So you can try to understand this as evaluating a linear combination of a column vector. So we can rewrite the above multiplication like this. So coefficient matrix and unknown matrix can be rewritten as this. So in this case, you have two vectors, and each of them led by a scalar value. So eventually, you are computing a addition of two scalar multiplication. And if you use this notion, you can try to see the same problem as a function. So from now on, you have a function that is represented using the coefficient matrix. And each input is x, and in our particular case, it was unknown. So this is the function, and this is the input. And as a background, let's try to understand the property, what is linear transformation. So the linear transformation can be defined as like this. So for arbitrary vectors x and y, there is a transformation t. And if and only if t satisfies these two conditions, then we say t is a linear transformation. So what is happening in the condition, you have two vectors, and individually you apply the transformation, and you took the sum. If the value is equivalent to the summation of two vectors applied to the transformation, then you satisfy the first condition. And you also take the scalar multiplication of the vector to the transformation. If the value is equivalent to transformation of the scalar multiplication, scalar multiplication of the transformation, then if you satisfy both of the conditions, then you say T is a linear transformation. And now let's extend it. So basically, these are the same notation as the previous slide, but were slightly expanded with vector. So for an arbitrary vector, instead of arbitrary vectors x and y, so for an arbitrary vector x1 and x0 and x1, T is a linear transformation if and only if T satisfies the following. So you have T here and original vector. And this vector can be rewritten as scalar multiplication of 1, 0 and scalar multiplication of 0, 1, each of them led by x0 and x1. So the original vector is the same as this. This is clear, right? And we want to satisfy the property of linear transformation. So based on the previous condition, we can separate the input into two pieces of output. So x0 multiplied by 1, 0, x1 multiplied by 0, 1, where they are separated, and you take the scalar multiplication of each in this form. So where everything is satisfied, then T is a linear transformation. And basically the notation makes sense, right? So to summarize, you originally have an input like this, and the output becomes somewhat like this. Now let's try to understand in the Cartesian coordinate, where 1x is here, 0, 1 is here, where it's getting dirty. So in the Cartesian coordinate, where 1, 0 is here, and 0, 1 is here, and they are meeting at 90 degrees, and they are unit vector, right? So they are orthonormal. But given that we have two coordinates, so it can be understood as x0 and x1 somewhere in the space. But basically still it is represented by the transformation into a coordinate system. So we have coordinate system led by 1, 0 and 0, 1. Now let's try to see the output in the same perspective. So we have x1 and x0, x0 and x1, and you have coordinate system transformed by t. So I don't know where this space is, but from now on, I have two different bases. One is t10, the other is t01. But given that, in this space, my data is represented as x0 and x1. So basically, a matrix can be understood as, well, from this to this. So you are transforming the space from the original one to the newer one. So this is what the statement on the top is stating. So every matrix can be understood as a linear transformation. So here comes an example. So this is actually coming later after we discussing eigenvalue decomposition. But well, here is an idea. So say A is a matrix. So A is a linear transformation. Well, after you take this transformation, where each of these dots, they are different vector. So you have, well, many vectors in, well, this side. And you multiply this transformation matrix. Then the result becomes like this. So, well, looks like, well, things are narrower along with the x-axis, and looks like things are wider along with the y-axis. So, well, what I'm saying, a linear transformation is sort of geometrically can be understood in this way. So, in this section, the important idea is, well, every matrix is a linear transformation. So please keep this statement in your mind. And things are getting more and more clearer after we study eigenvalue decomposition. So let's move on to it. So like we discussed, well, big background is a matrix is a linear transformation. And more specifically, well, we will see a linear transformation that consists of rotate and scale and rotate. So, well, eigenvalue decomposition. So if you have studied linear algebra, then, well, you may remember eigenvalue decomposition because this is one of the, well, largest and most difficult mob along with the course. Let's quickly read the idea. So every linear transformation has a unique transformation matrix. So every linear transformation means every matrix. It has a unique transformation matrix. And that becomes a special property. So where we want to find it using a analysis called as eigen analysis. And along with the eigen analysis, let us interpret linear transformation and their associated transformation mapping. So the idea can be written in terms of math in this way. So you have a original matrix A, and you have a eigenvector B. If you multiply A and B, it becomes a scalar value lambda multiplied by the eigenvector B. So basically these two are the same. So here B is eigenvector and this is important property, these are non-zero. And if you have n by n matrix, you can have up to n eigenvectors. But there is some matrix who has no eigenvector. And here, in terms of the notation, lambda is eigenvalue. So A is given. Given A, we want to find B and lambda. So in the previous slide, we talked about there is a unique mapping. So given matrix A, like we discussed, A is a transformation matrix. So any given vector on the space, it's going to be moved to somewhere else, or like this. But for A, for this transformation A, where there is a special vector. So it's a vector, so it has a direction. Where if you use one of the point on this vector and apply this transformation matrix, it's not going to left or right. It's only going to this direction or the other direction. That means it's going to be scalar multiplication, and that's it. And there is no rotation. So the idea can be carried in more semantic manner if you use this kind of analogy. So I actually brought a animation. So you are on the Earth globe and you are throwing a ball to the sky. Then if you are here, you are moving with the ball. So where your ball will go up and coming back. But basically, if you are looking at the moment at the third person position, Earth is moving, and I throw the ball to this direction, and it comes back to me. Basically, that means the ball is going to that direction and coming back to this direction. So there was two vectors. One is going up, the other is rotating. And the combination of these two actually decided the movement of the ball. Now let's think about the situation where you throw the ball to the sky from this North Pole. Then there is no movement from the Earth, right? You're basically just rotating in place. So your ball movement is just purely going up and down. So where in terms of eigenvalue decomposition, where the rotation of the Earth can be understood as the transformation matrix. And you multiply this to your movement, ball movement. And we want to find sort of this axis. So given a matrix, we want to find a sort of axis that the matrix has, the transformation has. And this is unique sort of, so this is called as an eigenvector. So in terms of the computation, here is the way you come up with the eigenvalue and eigenvector. So this is simply a system of linear equations. So you have given a matrix A, -5, 4, 0, 1, where you're writing down this form. So A, B, lambda B. And you can write the same equation like this, A negative lambda identity matrix multiplied by eigenvector B. Then you just solve it. So we can consider two different cases. One is B is 0. The other is A negative lambda I is 0. But the first case does not work because by definition, eigenvector is not 0. So only the second condition will acceptable. So we want to find lambda that satisfies the condition number 2. So here is the solution. So we're given matrix A, we want to multiply lambda and want to get the solution to it. And then you can easily write down this quadratic form equation. So this quadratic equation gives me two solutions, and these are my eigenvalues. And now let's take these two eigenvalues and apply it back to the equation here. And we want to address each of the cases. So when lambda is -5, we can write down things like this. And we can come up with vector 2 value here, vector 1 value, where someone like this. And take lambda is 1. This is the second case. And try to fulfill the value into the original equation and try to solve it. Then we can find the solution like this. So eventually you can summarize the result in this way. So we're given lambda, where this is my eigenvectors. So we're solving the original matrix, we're writing the original matrix A, where that is where someone like this, and where this is one way to write this down. And here comes the Python code, how to come up with the eigenvalue and eigenvectors. And here is one additional step that is called as diagonalization. So, and this specific form, so A, eigenvector, lambda, and eigenvector inverse, where this has also special meaning, so we'll talk about it later. Well, let's try to find out the meaning of eigenvalue decomposition again. So where we have seen this slide in the previous pages. So here comes the input matrix, and it can be decomposed into eigenvalue and eigenvectors. So we'll say this was a transformation, and it consists of two eigenvectors. So one is 0, 1, so 0, 1. So that is heading to the y-axis. And the second one is 1, 0. We're heading towards the x-axis. And we have the magnitude. So one is 2, the other is half, so 0.5. So this is the essential information that matrix A carries. So using eigenvalue decomposition, we can find it. And let's try to compare input and output of this linear transformation. So originally you have vector that are organized in a shape of a square, where along with the y-axis, you sort of doubled the value. So things become wider. And along with the y-axis, where you are making them half. So things are becoming narrower. So this is what the transformation is saying in essence. And this is a matrix called as, transformation called as a shearing transformation, where this is where some common shape, so where people use this format a lot in many examples. So if your matrix is like this, where basically you have only one lambda, and then lambda value can have two different eigenvector. So one is -1, 0, the other is 1 and 0. So you can draw one vector like this, the other vector like this, and their magnitude is both of them 1. In this case, the transformation works like this. So you are sort of pulling stuff to this way and pulling the stuff sort of this way. And the combination of these two becomes this. And this matrix is slightly different from the previous one. So previous one, this guy was 0, and this guy has half. So basically, when you apply eigenvalue decomposition, these are eigenvalues, and this is eigenvectors. So eigenvectors looks like this. Oh, sorry. And the first one, the magnitude 0.5, the other one 1.5. So basically, things are rotated in terms of the eigenvector. So this is compared to the original Cartesian coordinate, where things are rotated like this. So after transformation, that notation is also applied. So where you are basically sharing the stuff like this. And not only that, you rotated the matrix. So eventually you will have this result. And 1, -1, -1, 1. Lambda is 0 and 2. And you have two eigenvector, but one of the guy is magnitude 0. So maybe this guy takes any input and turn them to 0. So what's going to happen is, in this case, you are taking the direction of non-zero eigenvalue, and everything is along with the line that has the same direction to the second eigenvector. Well, we have seen the meaning of eigenvalue decomposition and try to look at the example of eigenvalue decomposition computation, right? And where we try to see the meaning of it in terms of the result as well. And let's try to take a look at one last topic related to it. So we started the discussion from here. So AB, lambda B. And lambda is a set of scalar values. And set of scalar value, actually, these lambda vectors. We can write this down in different format using in matrix. So basically, this is a diagonal matrix, means that you have lambda 1, lambda 2, lambda 3, and so on to lambda n. And the rest of the element, it just becomes 0. So you get the idea. So D is diagonal matrix. Everything on the diagonal is replaced with lambda. Everything else is 0. Well, given that, well, this notation, so lambda is simply switched to the matrix D. And when you had the scalar value in front of V, where the position of lambda actually doesn't matter. But since we have this diagonal matrix, where it has to be after, placed after vector B. Well, anyhow, well, after you came up with this, we can rewrite A, H, B, D, B inverse. And this has a special meaning. So let's move on to the next page. So what we just discussed, right? What we just discussed written over here. And one of the property of the eigenvectors, they are orthogonal. So when things are orthogonal, well, this is one of the property of the orthogonal matrix. So inverse of B is equivalent to B transpose. And when my vector set is orthogonal, like we discussed in the earlier slide, we can, well, this is just convention. We normally write them down in terms of P, using P. So A, B, D, B can be rewritten as A, P, D, P transpose. So these are just a notation-wise explanation, and let's now try to find what this actually means. So basically these two are the same. So let's try to see A, PDP, well, that is equivalent to PDPT, that is equivalent to B, D, P inverse. You have two input vector, P1 and P2. Yeah, P1 and P2, and you applied the matrix A. So every matrix is linear transformation. So you rotate it and sort of scaled P1 and P2 to somewhere in the space. But what is going to happen can be well, specified into this way. So where you are multiplying A to P1 and P2, well, just for example, where notation is, well, I just ruined the notation. So A, maybe this, and here P1 is, well, let's say in this way. So A multiplied by row 0 and row 1, and that is equivalent to P, D, P inverse row 0, row 1, right? And if you take a look at the multiplication of P inverse row 0, row 1, and D and the result, P and the result one by one, where things will look like this. So number one, you first multiply P inverse, then it's going to be, well, rotated. So P1 and P2 becomes E1 and E2 in this example. And then D, so matrix D was, well, diagonal matrix of lambdas, and it scales E1 and E2. So the shape of the circle becomes, well, sort of ellipsoid. Later on, you multiply P on top of it. So again, lambda 1 E1, lambda 2 E2 are rotated. So number 2, number 3. So the diagram over here is representing the matrix A is a linear transformation, consists of rotate, scale, and rotate. So this is sort of the nature of the matrix, and every matrix is supposed to have this kind of a property. And we are going to represent data and model where all of the components in machine learning using, well, basically matrices. So, well, it's very important to understand those, well, the fundamental properties. Well, after we decompose matrix A into PDP inverse, where some of the important quantity can be calculated very easily. So determinant is basically, well, production of the diagonal component, and, well, trace becomes the summation of the diagonal components, and rank can be found by the number of non-zero eigenvalues. And if A is symmetric and the matrix has two eigenvalues, two different eigenvectors are orthogonal, where there is some additional property you may study it in linear algebra. And one important concept is when A is positive definite, the eigenvalues will become all positive as well. And positive definite matrix is some special use cases in many places in machine learning, where here are some examples, but when it comes back, where we will discuss it later, but we'll try to be formalized with the expression positive definite. And later on, we are going to study dimensionality reduction. And one of the player in this region is something called as PCA and SVD. So SVD, PCA, these are two different dimensionality reduction techniques. So the idea is basically eigenvalue decomposition. So you have a data matrix. Using data matrix, you want to, well, sort of take the square of it. So D multiplied, well, D inner product of D transpose. This becomes something called as a covariance matrix. And if you apply eigenvalue decomposition to covariance matrix, you can get PCA. And if you add some additional condition, then you can get the result of SVD. Well, the PCA, using PCA, you can do something like this. So you can take only one vector from PCA, then things look like this. So we're getting some trend, but you get almost no idea from it. But if you get 10 vectors from the result of PCA, then you will get some rough shape of the original data. And as the number of the result of PCA vector you take increases, then the image becomes more clearer. So it can be understood as well, sort of data compression, and also well, more exact name of this technique is dimensionality reduction. So the idea of PCA taking the few vectors of the result of PCA, things like that, where you can take only a subset of the original data, and you can get the most of the information. But if you have all of the information, you get the every single detail, so that is still good. But if you don't have such a luxury, then you can take only this rough idea of the data. Well, that's sort of what this technique is offering. So we will come back to this topic after we study clustering and when we study dimensionality reduction. And this is some relevant topic, SBD. So PCA is one technique based on eigenvalue decomposition. SBD consists of basically two PCA. So there is some operation that takes two results of PCA, and you do something, but we will talk about it later. Eventually, you're going to decompose the original matrix A into three different matrices. And after you do this, you can decompose your data in really nice way. So this is actually one snapshot from the result from the data set name is BibTeX abstract. So what this data set includes is all the abstract of the academic paper. Especially in this experiment, we used the set of academic paper from computer science and medical domain. So you have the summary of multiple papers in your data set, and you took sort of representation for the text data that is called as bag of word. And you applied SBD on your data. And the result becomes like this. So you can separate the data in terms of the topic. So you can see by looking at the coefficient value, and especially these values looks like some block. So you sometimes just say this as block matrix. So by looking at the block matrix structure of your SBD result, you can try to find the cluster of your data. So in this case, where you can automatically find the group of CS paper, computer science paper, and medical paper. And you can also take the analysis on the vocabulary space as well. So I think I'm sharing too much detail at this point. So we will come back to this example later on. So we are going to discuss this example later. And there are some tools if you are interested. And maybe you will see these names a lot when you work in this domain. So if you try to implement linear algebra using C programming language or any other language, you have to use this library, one of these libraries, this linear algebra library, and they have been out there for a very long time, and it will not change it for at least a few years from now on. So this is a famous library for linear algebra.